MBA633 instructional video prepared by Professor Amit Dada, George Mason University. In this segment, we will discuss probability distributions and specifically discrete probability distributions. So recall that a probability distribution is nothing but a pattern of uncertainty associated with uncertain outcomes. And since outcomes can be of two types, continuous or discrete, you have two types of probability distributions. For example, I don't know how long it will take for me to commute to work tomorrow. So let's just say it might take between 30 minutes and 60 minutes, but it can take any time in between. So it's continuous between 30 and 60 minutes. And a different example would be, let's say I'm still commuting to work, but I'm interested in knowing how many police cruisers I might see on the way to work. Now that's a discrete outcome because I might see 0 cruisers, 1, 2, 3, or 4, but nothing in between. So that's the difference between continuous outcomes and discrete outcomes, both being uncertain. So in this segment, we'll concentrate on discrete probability distributions, just some properties that they exhibit, that they must, certain conditions that they must meet, and two different types of discrete probability distributions. So let's pick an experiment here, design an experiment. Experiment is just another way of saying it's a process that has well-defined outcomes, the outcomes being uncertain. So the experiment here is that I walk up to a person at random and ask them which day of the week they were born. So the sample space for an experiment is the set of all possible outcomes. So what possible answers could they give? And in this case, you know that there are only 7 possible outcomes, Sunday through Saturday. And it's discrete. It's one of those 7, nothing in between. Now, it's inconvenient to have to spell out these outcomes in narrative form every time we speak about them. So a very handy way of labeling outcomes is by using what's called a random variable. So it's usually we use the letter X, Y, Z letters towards the end of the alphabet to do that. So in this example over here, we have X equal to 1 is a shorthand for a person said their birthday is on Sunday. Similarly, X equal to 7 is shorthand for a person said their birthday is Saturday. So now the question arises, what is the likelihood that a person will say that their birthday is on Sunday or on Monday or on Saturday? Now, if we think about that pattern of uncertainty, one can represent that um, as a graph in the following manner. So I write the letter X as a shorthand for my outcomes, and X can take on the values 1, 2, 3, 4, 5, 6, and 7, the 7 days of the week. Now, if I didn't have any special particular information, I might be inclined to think that it's equally likely that a person might be born on Sunday or Saturday. If that's the case, then the likelihood of each of these outcomes is 1/7, and that's, I think, pretty intuitively obvious. There are 7 outcomes, so 1/7 is the probability for any one of these outcomes. By the way, the y-axis is the probability, that's the height of the spike. It's usually represented by p of x or f of x probability. Now, if you look at this picture, you see all the spikes are of the same height. Okay, so this distribution is what is referred to as a uniform discrete probability distribution. Why discrete? Because the outcomes are discrete. Uniform because all outcomes have the same probability. Now, the reason we drew it this way is because we have made the assumption that I don't have any special information that tells me that it's more likely that a person will be born on Sunday, or Saturday, or Monday. But that might not be the case. Suppose I go to the local hospital and then I actually get birth information of 1,000 births in the previous year. Okay, and I get the following pattern. I get the following table. Let's say I won't draw all of them, but so let's say I look at 1,000 births in the previous year, and I find that out of those 1,000, 100 were born on Sunday, x equal to 1. Okay, and I find that 200 were born on Monday, and I find another 100 were born on Tuesday, and I find that 300 were born on Wednesday, and so forth. Okay, so 7 will be something, and these will add up to 1,000. Now remember the concept of a relative frequency that we had talked about very early on. So in terms of probabilities, if this is the raw data that I collect, then the probability of a person being born on Sunday is, from here I can deduce, is 100 divided by 1000, which is 0.1. Similarly, the likelihood of a person being born on Wednesday, Sunday, Monday, Tuesday, Wednesday, here is 300 divided by 1000, and that's equal to 0.3. Now, if I compute these numbers and I draw the graph again, so again I have x as my random variable. This is shorthand for the outcomes for this experiment, and I have the outcomes as 1, 2, 3, 4, 5, 6, 7. 1, 2, 7. Now you find that all the spikes are not of the same height. So the first spike probability, its height is 0.1. We had just calculated it here. Okay, and the second spike is a little bit taller, and the tallest spike is x equal to 4, and it's this one. Okay, so if you look at these two patterns, both of these patterns of uncertainty are discrete probability distributions. Just that one, the first one is uniform, the second one is not. Now, regardless of what a discrete probability distribution looks like, it must meet two properties. Okay, the first property is that there are no negative spikes. So every spike that you draw must be greater than or equal to 0, and that's very simply, the justification is very easy to see. Since probability is measured between 0 and 1 inclusive, you can't have negative probabilities. Okay, so that's what the first constraint is saying. The second one is the more important one, really, and it says that if you add up all the spikes over the sample space, in other words, if you add up the height of all the spikes across all possible outcomes from the experiment, then they must add up to exactly 1, nothing more, nothing less. If it adds up to either less than 1 or more than 1, something has gone wrong in the assignment of probabilities. So these are the two properties that must be met by any discrete probability distribution. Okay, but notice one thing, in this experiment, the outcomes are certainly discrete, but they're also finite. I know that there are 7 outcomes. Now, if you reflect on it a little bit, if you have an experiment that has a finite number of outcomes, by definition, it has to be discrete. You can't have a continuous distribution with a finite number of outcomes. Okay, that sort of defeats the definition of continuous. So this is an example of a finite discrete probability distribution. You can think of many others that fit this mold, and we will see other examples of this when we get to quality control. So let's look at another variant of discrete probability distribution with a different experiment. Okay, so here's a different experiment that we're looking at. I pick up the Washington Post on any morning, and I read the newspaper, and I just count how many vehicle accidents have been reported in the paper. Okay, so again, just as in the previous case, we use a shorthand, the letter X, to label the outcomes from this experiment. What possible outcomes could you have? So you read the newspaper, and you might find that on the particular day that you read it, no accidents have been reported. So X could be 0. Or the newspaper reports 1 accident, or it reports 2 accidents, or it reports 57 accidents. Theoretically, do you see, this newspaper could report a an infinite number of outcome. So this really could go to infinite. Obviously, the likelihood that the newspaper will report that there have been 10,000 accidents or even anything close to that is practically zero. Okay, but theoretically, the newspaper could report an infinite number of accidents. So notice that this experiment has a discrete number of outcomes. So you can have one accident, you can have two, you can have three. You cannot have 3.5 or 4.25 accidents. So it's discrete, just like the previous experiment, but unlike the previous experiment, this one has an infinite number of outcomes. Okay, so this is a discrete infinite um, a type of experiment and a type of distribution. Okay, so now suppose I look at data over a year. Let's say I look at the newspaper every day for 365 days and I count, just like in the previous experiment. So out of those 365 days, I find that on 2 of the days, the newspaper reported there were no accidents. Okay, and on 15 out of those 365 days, the newspaper reported that there was one accident. And on, let's say, 50 out of those 365 days, the newspaper reported that there were two accidents, and so forth. And we go up to 5, let's say, and on 75 of those days, the newspaper reported that there were 5 accidents, and so forth. And I suspect, as a practical matter, if you go beyond 15, it probably would say 0 beyond that. Okay, but once you get these numbers, you can compute a relative frequency. Okay, so here, out of those 365 days, on 2 days you had no accidents. So the probability is 2 divided by 365. In the second, for x equal to 1, the probability is 15 divided by 365, and so forth, and you would get all these relative frequencies. And now if you plot the distribution, again you have your x. The main distinction with the previous distribution is that x can take the value all the way up to infinity. Okay, and you have spikes of different heights, so they look like this perhaps. So you have an infinite number of spikes. Regardless of the fact that you have an infinite number of spikes, the two rules that I told you, namely that no negative spikes, every spike must be 0 or higher, so no negative probabilities. And if you sum up these spikes, the heights of these spikes, across all the infinite number of spikes that you have, they must add up to 1. Okay, so here are two different examples of discrete probability distribution that I've given you. Okay, you can think of lots of examples of finite and infinite discrete distribution. Insurance companies, for example, deal with this kind of probabilities where they're dealing with accidents, or number of deaths, for example, and there it's discrete. You can't have 2.5 deaths, but the number of deaths could be 0 through infinite. Okay, theoretically at least. All right, and in some cases the number of outcomes is finite. So there are two different types of discrete distributions. One is finite, one is infinite, and that depends on the number of outcomes that you could have from the experiment. Regardless, there are two rules that any discrete distribution must obey, and these are the two. You can't have negative probabilities, and the sum of the probabilities over all possible outcomes is exactly equal to 1. Now, there are two common types of discrete distribution that fall into these two categories, and there are video clips on those separately. One is called the binomial distribution. It is a discrete probability, finite probability distribution, and then there's the Poisson distribution, which is a discrete but infinite probability distribution. The former has a lot of applications in quality control, and the latter has widespread application in congestion control and service level management. Okay, so this is a summary sort of on discrete probability distributions.